If we have a mass m at distance r1, then we know that its orbital velocity is v1 equals square root of gm over r1, obtained by setting net force equal, well, the gravitational force equal the centripetal force. Net force is the gravitational force, and we just set the expressions for those two quantities equal, and we easily get v equals square root of g over gm over r, big G, big M over little r. Big G being the universal gravitational constant, big M being the mass of the planet, little r being the distance of the circular orbit from the center of the planet. This leads directly to the kinetic energy expression, which will be M over 2, big G, big M over R1. And that's just 1/2 big G, big M, little m divided by R1. Same expression at distance R2. Of course, replacing R1 by R2. So the change in kinetic energy is this minus this. So you can read the expression. It's very obvious. Okay, change of potential energy from R1 to R2 is equal and opposite to the work done by the net force. So negative here for equal and opposite, net force being in the direction opposite our motion from R1 to R2. If R is in the positive direction, then the net force is in the negative direction. So we have the negative here. So the net force acts in the direction opposite, increasing R. Okay, so we do the integral. The integral is very simple. Just the power function, factor out the negative big G, big M, little m over, the negative big G, big M, little m. Then that negative is going to make that positive. You're going to have the integral of positive 1 over r squared. That's a simple power function. Its antiderivative is negative 1 over r. So we get this expression, big G, big M, little m over r, evaluated from R1 to R2, which gives you this expression. Now, this expression is identical to this expression, except for the 1/2 and the fact that both of the signs here are opposite what they are here. We quickly conclude that the kinetic energy change, if we move from one circular orbit to another, is equal to -1/2 of the potential energy change. That is, okay, if we're moving from a lower orbit to a higher orbit, the potential energy change is positive. The kinetic energy change is going to be negative and 1/2 the magnitude of the potential energy change. It's a very important idea. You move further, you don't orbit as fast. Obviously, when R increases, V decreases. So you lose kinetic energy, but it takes energy to get from here to there. So even though you're losing kinetic energy, you've still got to supply enough energy to make up the difference related to the potential energy. That is, you got to increase the potential energy. But you don't have to do all the work required to increase potential energy because you're losing kinetic energy. So you basically have half the energy. You're basically losing half the potential energy. You're basically losing enough kinetic energy that it supplies half of your potential energy depth. Okay, so that's an important idea. I'm just looking at this. I'm going to pause for a second. Okay, we want to find the energy needed to take a mass from the surface of the Earth to a circular orbit at distance r, above, or distance h, above the surface. So, in the first place, if we launch from the right place, we have some kinetic energy from the Earth's rotation. The Earth is rotating. If we launch in the direction of the Earth's rotation, we've already got some kinetic energy then. Now, the velocity we need at distance r from the center is, of course, square root of gm over r. So if RE is the radius of the Earth, H is the height above the Earth at which we want the orbit to occur, and hopefully we do that above the atmosphere. Very inconvenient to try to orbit within the atmosphere. So the radius of the orbit is going to be radius of the Earth plus whatever height we want. So the velocity at that distance is what? Square root of gm over RE plus h. So now what's the kinetic energy? Well, that's going to be very easy. Just assume mass little m and do 1/2 mv squared. So we get that very quickly. The potential energy change from R1 to R2 is, as we saw here, big G, big M, little m times, it's -1 over R2 plus 1 over R1. I do 1 over R1 minus 1 over R2, same thing. And that's equal to what? We add this to this. Actually, we add this to the change in kinetic energy between here and here. This is going to be a fairly insignificant amount of kinetic energy. But since we're dealing with a situation where we can just barely get a payload into orbit, that little bit of kinetic energy helps. Okay, so that's a very easy way to solve the problem. It's very straightforward, just fill in the blanks, and we have that result. Now, I'm not going to write out the rest of it. I have this little note over to the side here. It's kind of parenthetical. We just wrote this to clarify what I mean by V of R, that V of R is V as a function of R, not V multiplied by R. Of course, we know that. But just to be sure, I did V of aardvark, okay? R sub the vark. And that's GM over aardvark. Okay.